Okay, so let's get going. So today, I hope to finish the data distribution correlation section. We're a little bit behind from what I was the last time I taught this course. I think it's because I've been talking at the beginning of class about other stuff. I'm not worried about finishing all the material. We'll get there. But I do want to make sure that we take enough time to review for the test. So what we're going to do is just do a little bit more of the notes, review for the test, and if there's still time, we'll come back to the notes. Regarding project number 1, I want you to get this now, start thinking about it. Next Tuesday, we will actually talk about it in class. Again, this will be group work. At least for this project, I want you to work in groups of up to 4, so 2 to 4. Because I think you can learn a lot from your fellow classmates, not just from me. And it also emulates what you often have in the real world, where it's not just you working on something, you're working in a team. And what project number 1 will be over is not stuff that we've gotten to yet. It's going to be the graphics section. So we'll look at how to graph multivariate data, and also something called the principal component analysis section, which we might talk a little bit about what that means later today. My original plan that I actually have mentioned is to use your own data for it. And there's a variety of different ways to get your own data. I'm not for sure if I'm going to stick to that plan. The reason being is because I would expect in this class there will be 10 plus groups with all their own data. And what I would ask all of you to do is email me the data first, and we would have a conversation about, is this data appropriate? How would you actually approach analyzing the data? And so as you can imagine, that will take a lot of time. Also, grading projects like this takes a lot of time because everyone has a different data set. Since I found out the official news about the department on Thursday, I've been basically working all evenings, all weekends, doing stuff so that we're ready to go for our appeal, so that the department's not eliminated. That's taking a lot of my time. And so I might end up giving you instead, all of you, one data set to work on. It'll be easier for me to grade and communicate with you about it. Now, there will be a week number 5 quiz that's due the usual Wednesday. All this is if you do it, you get 5 points. If you don't do it, you get 0 points. And I just want you to indicate who your group members are, or if you need to be in a group. Or if you're not in a group and you want to be in a group, or you want my help to get you in a group. I'll help you do that. So I understand that there's probably a lot of you who don't know anybody else in the class. So I will help you do that. And so start thinking now, who you want to have in a group if possible. Are there any questions about the material before we get going in the notes? Okay. So we were talking about standardized data. And all this means is that we take our data value, subtract off the estimated mean for the corresponding variable, divide by the square root of the estimated variance for that variable calculated from the data. And so what we end up getting is a unitless measure. We're no longer talking about feet or gallons or anything like that. It's unitless. And because of that, we can make comparisons from one variable to another as a measurement of, let's say, how close they are to their own means or how far apart they are from their own means. And so something that I didn't actually have in the notes I want you to make sure you have there is that basically what we're looking for is the number of standard deviations a particular data values from the mean. Why? Well, notice what we're doing. We're taking x, subtract off mu hat. Well, the distance from the mean, and then we rescale it by the standard deviation. And so if I had, for example, suppose the top here was equal to 2. So maybe I had 10 as my observed value, 8 was my mean, 10 minus 8 is 2. And suppose then the standard deviation, or the square root of the estimated variance, was 1. And so what that would tell me is that 10 is 2 standard deviations from the corresponding mean. Okay? The more standard deviations you get from your mean, the more unusual that particular observation is. You know, if you've heard of, you should have heard like something called like the empirical rule, or Chevyshev's theorem, especially if you've done a mathematical statistics course. And I like to lump that all into, at least for, I do it with introductory students, but we can do it here too. I like to lump that into what I call the rule of thumb for the number of standard deviations all data lies from its mean, which is 2 or 3. So if I'm more than 3 standard deviations from a mean, like maybe like a serial data value, a sugar value, that says that that serial content, again, if it's sugar, that sugar content is unusual compared to everything else that's in your data. It's an outlier. Okay? So these standardized values, Z sub R, J is our notation. The R says the rth experimental unit, or you could say the rth observation for us. The J corresponds to the variable. And we can put all those Z sub R, J's into a nice matrix. We'll just call it Z. So if we go take a look at our serial data set again, just to review, remember we had to adjust the serial data values by their serving sizes. So the first line of code here is I read in my data. Then I could do a head of my data that's in serial just to verify that indeed it looks right. Yes, it does. And then to find this adjusted sugar value, I take this, the sugar number of sugar grams for each observation, divide by the serving size for each observation, and I create a new variable in the serial data frame called sugar. Serial $sugar creates that new variable. I do the same thing for fat and sodium, and here I go. Here's my data within the adjusted values. Sugar through sodium are in the 8th through the 10th column of that data frame. Knowing that, then, I want to find some standardized values with it. And to do that, there's a function R called scale. Why is it called scale rather than maybe standardized? Well, scale, we're rescaling the data values. That's where the name comes from. We're rescaling the data values so that what they will have is a mean of 0 and a standard deviation of 1. That's something we did talk about last time, but I didn't mention that in the review. So these Z sub R J's, all of them for variable J, if you add them all up, and divide by the number of variable values that you have, you will get 0. So the average of the Z sub R J's will be 0. Their standard deviation will be 1. We'll look at that very shortly. But what scale allows you to do, if you wanted to rescale it so that it has, let's say, a mean of 5 and a standard deviation of 10, you could do that too with the scale function using some other arguments inside of it. Rarely would you ever want to do that, but you could do it. So we're just going with the default, so that's why you don't see these arguments, and just simply scale. And again, columns 8 through 10 contain my sugar, fat, and sodium values. I put that into something called Z, and let's take a look at the head of it, and there we go. Okay, so what I could do is actually double check, is this 0.452841 correct? So what I would do for that data value, I go to my original sugar, 0.357, subtract off the sample mean, divide all that by the standard deviation. And that's what I do here. Serial $sugar minus the mean of all the sugar values, which is 0.289. Divide all that by the standard deviation of those sugar values, which is 0.14. And so if I put that into Z.sugar, notice I get 0.45284, exactly the same as what you see there. That was in my Z data frame. Okay? And just to show you that indeed, if I were to take the mean of all these sugar values that are standardized, look at what my mean is, just about 0. What's my standard deviation? 1. Okay. And that's just going to be, again, the same for fat and also for sodium. Because it's the same, that's why we can make now comparisons across the variables. I could also find the estimated covariance matrix of these standardized values as well. And to do that, I use the co-function that we talked about last time. So it's the estimated covariance. So 0.2397 is the estimated covariance of, I'm going to use some informal notation here. Let's say Z sub sugar, comma, Z sub fat. 0.2397. Also, we could do the correlation matrix. So here's the estimated correlation. Okay. So you're going to see some interesting things there. Let me just double check. Yeah. Why is the estimated covariance matrix equal to the estimated correlation matrix here? Why do you think? It's kind of weird. We didn't have that before when we were dealing with the x's, but we have that here for the z's. Why?
Because the denominator of the correlation function is going to be 1 because of standard deviation.
Exactly. So if we look at, let's say, the true correlation, so this isn't the estimated, let's say the true, and let's say we just have two variables called Z1 and Z2 that are standardized. Then we have the covariance of Z1, Z2 over the square root of the variance of Z1 times the variance of Z2. Well, what's the variance of Z1? 1. Variance of Z2 is 1. That's why we have this happen. Okay. Also notice the estimated correlation matrix is the same as the estimated correlation matrix that we had previously for the x's. You can go back and see that on your own. But trust me, it is the same. Why do you think this happens? This is a little bit more difficult. It helps if you've had a mathematical statistics course to answer this question. So because of that, you're not required to be able to, let's say, prove it here, because a mathematical statistics course is not a prerequisite for this course. But you are required to understand that this result happens. This will actually play a very important role for us in the principal component analysis section. So for those of you who've had a mathematical statistics course, why do you think this occurs? Okay, so what I've written there is the covariance for essentially Z1 and Z2, but I've actually put in what Z1 and Z2 are. For those who've had a mathematical statistics course, what's going to happen to this part there? Think about what happens when you have a variance. You're trying to find the variance of let's say if you're trying to find the variance of, let's say, 2 times x. What would how could you simplify that? Exactly. 4 times the variance of x. Okay. If you haven't had a mathematical statistics course, that's okay. You don't need to know that. But the same thing's going to happen with the covariance. I'm going to be able to pull that out. I'm going to be able to pull that out as well. Okay. In a math stat course, you actually we'll learn something like this too. Let's say I have the variance of x plus 2. What is that equal to? just the variance of x. Because how can the number 2 have any variability? It's just 2. Okay, that's the intuitive explanation. And so guess what's going to happen here? Boom, boom. And so the covariance of z1 and z2 ends up being the covariance of x1 and x2. Plug that into the correlation formula, and voila, you get what you need. Okay? Okay, so this is where we're going to stop for now in terms of the new material. Next, what we're going to do is talk about the tests. So usually the way that I do like test reviews, I don't have specific notes associated with them that I distribute online. So if you want, you should take your own notes here. Do note that there will be recording that will be available so that if you miss something, you can just go back to the recording. So for test number 1, it will be the material up to the end of this section that we're just doing here. If we get to this last part of the notes. Otherwise, it will be to the end of what we just talked about. Okay. As I said before, close book, close notes, close video. So the only thing that you can use, yes?
You mentioned you give us some formulas, not formulas, like syntax for R functions. Is that still the case? Or?
Yes. So if you go to my graded web page on my main website, you will see a PDF file that's called something like functions and formulas. And so that's what actually I was going to talk about right there. So you will have access to that. And that can be like a quick guide for, okay, what's the function that I use to standardize data values? Scale. Okay. You will have access to all my R programs. You can have access to the R help. Do note that I will remove all my course notes from my web page before the test. You'll do the test on these computers here. If you haven't done this already, I recommend before you leave to actually log on the computer just to make sure you can do it. Make sure you see that RStudio is available. Regular R is available as well. 10 is not available. Word is on these computers as well. You may need to install packages to do the tests. I will make the test available as a Word file on my course website, the graded web page at 1225. So if you want to start early, get to class early, and you have essentially 5 extra minutes. So again, you'll download a Word file for the graded web page, put all your answers in this Word file. There will be equations that you might have to type out. I understand not everyone is as good as typing out equations as I am. So I am okay if you use, let's say, a text-based equivalent to an equation. So for example, maybe you need mu hat sub j. So what you could do for a text-based equivalent, you could say mu hat, I don't know, some people put an underscore j. If you just put a j next to it, that's probably fine too. You could type something like that out. But do note that mu is different from mu hat. So I would take, if for some reason a problem required you to put mu hat there and you put just mu, you would get a little bit off. Okay? There is a difference between the estimator and the parameter value. Our class normally ends at 1:45, but you're welcome to take up until 2 p.m. to complete the test. There should be no one coming in this classroom after us, so that's why I'm giving you that extra time. At least on the schedule, there is no one. Now, to actually turn in the test, sorry, I thought I had this up, but obviously I did not. Under quizzes, you're going to see test 1 fall 2025. Let me turn this to a student view. So test 1, 2025. Oops. Let's see here. Let's reset student. I was playing around with it last night just to make sure everything worked, and I turned in something. So let's do quizzes again. Test 1. Take the quiz. It's actually a test. And what you'll do is simply upload your test that's completed. Please make sure you put your name in the file too, just to make sure. Choose your file, find it on your computer, and then don't forget to do this. Submit the quiz. I will not have access to what you've turned in unless you do submit quiz. Don't forget to do that. Any questions about that? Okay. Now, we do know that computer technology sometimes fails. We do have extra computers in this classroom if that were to happen, so that's good. But if everything really goes bad, I'm willing to let you use your laptop. So bring a laptop, just in case. Probably the number one issue that sometimes students will have with these kinds of tests, I've been giving them for many years, is speed in completing the problems. So if it takes you 15 minutes to figure out how do I find a quantile from a standard normal distribution, then that's taking you too long. You do need to build up enough familiarity, that's maybe not a strong enough word, enough of a background to do this stuff in a timely manner. So please take note of that. We will have an example question coming up so you see what it looks like. So that's the basic format for the test. Any questions? Okay, so now the structure. Every single problem that requires a computation, you need to show your work. So that could mean you type out a formula, or what more often will be is you will need to show me all your R code and output that's used to do a calculation. The reason why I require that is because I can give partial credit. If instead you just, let's say, gave an answer of 2.5 and the answer was 3.5 and you didn't show me how you got 2.5, it's hard for me to give you any partial credit because I have no idea what you did. But if I see your code and I see that, oh, you just made that one little small error there, you're going to get a lot of partial credit. So that's why I do require you to show your work. Again, all R code and output that you do needs to be in there. I guess I kind of said this example already. Suppose you need to calculate an estimated covariance matrix. You will not receive full credit if you only give the matrix itself. I need to see how you calculate it. In other words, show me that you use COVE. Problem types. Typically, most of the problems on my tests are multiple part problems where there's some central focus given at the very beginning. It could be, here's this data set that we're looking at, or maybe like for us right now, here's this multivariate normal distribution that we're looking at. Answer parts A through D based upon this setup. So you perform calculations, do interpretations as necessary. And then my last problem on the test is always a short answer problem set, where there might be, let's say, parts A through D, or maybe A through F, or whatever, where each part is not interconnected in any way. They're totally separate from one another. And these kinds of problems help me narrow down certain specific things I want to assess of students. So let's take a look at an example problem that I've actually given before on a test in this class. So this is a multivariate normal problem. Suppose X has this particular multivariate normal. Complete the following. Part A, which of the plots below is the correct contour plot for the distribution? Explain your choice by specifying particular characteristics of the plot that correspond to this distribution. So what might be the first thing that you do here?
Check if the means are in the right spot.
Exactly. There's two ways to approach this problem. The first one is to do it without our code. See if it can be done. So notice the means are 5 and 10. So this one could be okay. Let's see now. This one could be okay. This one could be okay. This one cannot be. Because notice the mean of x2 is not 10. Okay, so now we've eliminated one. Then we take a look at this here. How about we calculate the correlation of x1 and x2? It's going to be 2, it's going to be 1 over the square root of 2 times 2. So 1 over 2.5. Okay? So notice it's positive. And if I have a positive correlation, what would I expect for these contours? Should they, let's say, be like this or like that? Like a positive, it should be like a positive relationship. And so, boom, that goes away. And this is greater than, obviously this is greater than 0. And what we know about the multivariate normal is that if I have something where I just have plain old circles, like this, the correlation is going to be 0. So then that means, get rid of that, here's my answer. That's one way to approach it that doesn't require code. Another way is to actually do the code, to actually do the plot yourself. And so I recognize that probably none of you have memorized the code to do one of these contour plots. I couldn't do it off the top of my head either. And so I would think, okay, now where did Chris do one of these plots before? Oh, I think it's the normalplot.r program. So I'm going to download that program to my computer, find where he did one of these plots, make some small adjustments to the code, corresponding to, well, I have a mean of 5, I have a mean of 5 and 10, here's my covariance matrix. And then I use that as a template then to run my code, or I first call it a template, change the code, run it, do the plot. And that's how you can answer it. So let me show you what I have here for an answer. Okay, I guess the way that I did it here is I reasoned through it. Later, I did actually needed to use some code later to do some stuff. So then part B, roughly indicate on your chosen plot from A where you would expect most of the x1 and x2 data values to be from a random sample. Now, depending upon how good you are in Word, you could probably copy and paste this plot down and somehow, actually do something like this. Or you could just describe to me. I would expect most of the points to be centrally located towards the smallest ellipse. And as I go out from that ellipse, the points become less dense, let's say, more scattered. But I would expect most of them to still be within this ellipse kind of a format. I wouldn't expect anything, for example, over there. And so you could just use wording. That would be one way to handle it. Now, a longer way to do it is what I actually also included in my answer key was I actually went ahead and did it. It wasn't needed. Notice that would probably take me more time, but one could do it. Next, on the plot chosen for part A, plot the eigenvectors for the covariance matrix. Scale the eigenvectors so that they have a length of 5. So, again, in my program, you'll see, okay, there is a, hold on. This is actually material that we have not done it yet. This is the next set of material in my notes. So I'm going to take that out for now. Sorry about that. But we talked about eigenvectors before and be able to graph them. So you should be able to actually graph the eigenvectors. What you will find out in the next section is this cool little thing, is that these eigenvectors point in the direction of what's called the major axis of the ellipse and then also the minor axis of the ellipse. And this is going to be very important to us as we go along, especially for the principal component analysis section. And then lastly, find f of x at x equals 6 and 11. So in other words, just plug in this vector into this multivariate normal equation, find f of x. One way to do it is to actually do all the matrix algebra. That would take more time than what's actually needed. The easiest way is to use the MVT package, get the corresponding function from that we've used to calculate f of x, and then it'll be really quick. So that's an example of one of these problems. Hopefully this doesn't take you more than 15 minutes. If it does, then you'll have to see what happens on the other parts of the test. So an example short question. What is the difference between using the asterisk and the percentage asterisk percentage with matrices in R? So one sentence. One is for element-wise multiplication. The other one's for standard matrix multiplication. That's it. That's an example short answer question, or and maybe I didn't explain this very well. The last problem on my test is where you have a number of parts that the questions in there are not interconnected. Typically, these are short answer questions. I might not put that part in there in my previous description. They're short answer questions where we might have to say one or two sentences, okay? So, specifically for this test, I'm going to actually give you some ideas what it's going to look like. Now, the test is not finalized. Normally, I would have it finalized by now, but I've been busy with a few other things. But it will be finalized soon. The first problem number 1, is a simple linear regression problem. There's going to be some similarities to what you see in the part 3 of my introduction to R notes. There's also going to be some matrix algebra stuff as well. There's 3 or 4 parts to the problem, and I'm going to give you a data set to work with. So you have to download the data set from my graded webpage as well. So that's problem number 1. Problem number 2. For a probability distribution that is not a normal distribution, I want you to find a quantile or a probability in R for it. So the reason why I have this problem here is that while we've only done this with a normal distribution, this is meant to assess your ability to use the R help. So I know what classes all of you have taken before, and I know what probability distributions that you've seen before. So it's going to be some probability distribution that you've seen before. There's going to be a very limited number of distributions I can choose from. So you could probably write out, I've seen this distribution, I've seen this distribution, I've seen this distribution. Let's see if I can answer the corresponding question that Chris just said in R. So find a quantile or probability, and then plot the distribution to scale, just like what we did with the curve function with the normal distribution. So just a probability distribution that all of you have seen before. You've not seen any other probability distribution before? Just give me one, come on.
Uniform.
Okay, uniform. Well, not everyone's seen a uniform. That would be, did you see it like in a mathematical statistics course?
I was thinking about looking at very point.
Okay, well maybe you have. I will tell you, it will be a continuous random variable. So it's not even going to be a binomial. It's not going to be a uniform. Give me a probability distribution for a continuous random variable that you are fairly confident that you would see like in a Stat 218, Stat 801 type of course. Poisson's not continuous. Sorry. So Poisson's not on the test. chi-squared. Okay? So what you could do is think about, how do I find a 0.95 quantile from a chi-squared distribution? Or how would I find the probability that a chi-squared random variable is, let's say, greater than 3.84? How would I find it with a particular degrees of freedom? So, you think about, well, what functions in R would allow you to do that? You could do a little bit of a search in the help, get the corresponding function, and do the calculation. Then think about, how would you plot that distribution? Again, there's a limited number of probability distributions that all of you would have seen before. I know you might be thinking, well, geez, Chris, I haven't taken all the other courses that everyone else has. I don't know their background. That's true. Think of it from the perspective of a Stat 218, which is like your first, well, for many students, your very first ever stat course that you take. Or a stat like 801. If you want to know what a stat 801 would look like, take a look at my course notes that are online. Then problem number 3, you're going to do some stuff with a multivariate normal. I just showed you one example what one of those kinds of problems would be like. So be ready to do some kind of graphing, for example. Problem number 4, you're going to be working with some matrices. Maybe actually have to, I shouldn't say maybe, you're going to actually have to type out some matrices. So I want to make sure that you understand what's actually inside some matrices that we were looking at. And then the last one is some short answer questions. Those questions that are not connected anyway. That's what the test looks like right now. If there are modifications, it will be small. Any questions? Do you want me to be more specific about these questions up here? Sorry, can't go that far. Yes?
Is this document that has this somewhere for us to see or no?
It is not.
Okay.
Yeah. So the key thing is, one reason why I don't do this is because I'm often making changes to it, like right before class or something like that. And since it's being recorded, if there's something that you need, you can always go back and look at it. And this also, to some respect, is to help encourage you, because you're probably not going to catch everything that I'm saying right now. Okay, so let's take a look at review the material. So there were like 3 main sections. The first one is Introduction to R. We first actually in class started talking about what's the basics. What is a function? What is an R function? What's the very last line of a function? Why is that so important? How do you find items and help? What is an argument? Some of this is like, you need to make sure that you actually understand the proper terminology, so it's easier for you to communicate with someone else who's also doing stuff with R. So vectors, packages. We talked about various program editors. Obviously, I'm not going to say use 10R for something. I can't, because 10R is not on here. But I might say something like, well, what are some possible program editors that we could use? Okay. The main thing is, I want you to make sure that you do know there's something more than RStudio. Welcome to use RStudio, but there's more out there. Then there was a regression example, being able to read in data, do a scatter plot, estimate a regression model, stuff that you would have seen in another class. You may or may not have actually used R for it, though, in the past. And then lastly, understanding that R is an object-oriented language, and so the class of an object plays a very important role with respect to generic functions and method functions. So I could ask you, what's the difference between a generic and method function? Or I could simply ask you, why is a class of an object so important? Or when a generic function is executed, what's essentially the first thing it's going to do? not going to check the class. Well, why? To find a corresponding method function. Next, we did matrix algebra. The basic structure of a matrix is important. All the stuff that we did with with simple linear regression is important in this context too. Some basic definitions, like what is a transpose of a matrix? What is a symmetric matrix? What's the diagonal of the matrix? What does it all mean? How would you find the inverse of a matrix? R and by hand if you're doing a 2 by 2. The by hand equations are in my formula sheet. What are eigenvalues and eigenvectors? Then we got to the data distributions correlation section. We introduced the whole basic concept of multivariate data. We introduced how I can put my data into a matrix. And then we talked about the most important multivariate probability distribution out there, the multivariate normal. Make sure you understand like the mean vector, the covariance matrix, the correlation matrix. Maybe give me, when we talked about covariance, we talked about it from an intuitive point of view in terms of the expected value of, let's say, x1 minus mu1 times x2 minus mu2. Can you explain what a covariance means in the context of this equation from an intuitive point of view? We talked about how if x1 tends to be larger than its mean, just like what x2, or just like x2 tends to be larger than its mean at the same time, then that means you're going to have a positive number times a positive number. You're going to have a positive value as a result. If the same thing happens with when x1's less than mu1 and x2's less than mu2, what's going to happen? You're going to get a negative times a negative. You get a positive, and this you would expect a positive covariance value. What does a positive covariance mean? It means you have a positive relationship between the two variables. Make sure you're familiar with that f of x expression. How can you plot the distribution? How can you simulate data from a distribution? I could ask you a question about, well, why is data simulation even important to begin with? And that could be like a good short answer question. Or I could ask you, say, for this multivariate normal, simulate some data, show me the first data value that's simulated to prove that you did it right. Then once we have these data values, we might want to do some summary statistics with it. Now we have what's called the estimated mean, the estimated covariance. We have the estimated correlation. As the sample size gets bigger, what's going to happen to these estimates? They're going to get closer and closer and closer to their true values. Again, while you're not responsible for this part, I'm just going to say right now, this is an example of the weak law of large numbers in action. How would you check multivariate normal? Well, unfortunately, there's not a good way to do it, but we have some ad hoc ways to try to do it. We just got done talking about standardized data, and then hopefully we will get to the eigenvalues and eigenvectors. Okay, so that's all I have to say specifically about the test. Are there any questions? I don't try to make tests hard. I do my best to make it so that you should be able to complete it in an hour and 15 minutes, but I always try to give some extra time if needed. And so that's what I'm trying to do here by letting us, go a little bit longer. I think the number one thing that students say after they take one of my tests and they don't do as well as they had hoped, they say, I understood all those problems, but I just didn't study enough. I know we did something like that in class, Chris, but for some reason I just couldn't do it on the test. So I guess what I'm trying to say, there shouldn't really be surprises. other than what probability distribution you're using for that one problem. Any other questions? Okay, let's finish up this data distributions and correlation section. So now we're going to start seeing why these eigenvalues and eigenvectors are important. And we're going to work with the covariance matrix for a multivariate normal. We're going to find the eigenvalues with it. We're going to let lambda 1, lowercase lambda 1 be the largest of those eigenvalues. Lambda 2 is going to be the second largest, all the way down to lambda sub p. We go down to p because this sigma is a p by p matrix, because we always have p variables in a general sense. Each eigenvalue, of course, has an eigenvector associated with it. These eigenvectors and eigenvalues are going to tell us something interesting about the probability distribution. I guess in particular, that's actually what's next here. Okay. So suppose you have a bivariate normal distribution. Again, that means you have p equal 2. The spread and the direction of contours on a contour plot for that distribution are related to the direction of the eigenvectors. I was kind of alluding to that earlier. In particular, the first eigenvector, which corresponds to the largest eigenvalue, the eigenvector actually points in the direction of the major axis of the ellipse created by the contours. This is the direction, you could say, of the largest variability for that probability distribution. Then the second eigenvector, which corresponds to the second largest eigenvalue, points in the direction of the minor axis of the ellipse created by the contours. This is the direction of the smallest variability. So let's actually take a look at a plot. So here's our multivariate normal distribution that we've seen before. There's going to be two contours on it at 0.01 for f of x and 0.001, which we hadn't seen before. I'm going to put the eigenvectors on the plot with a length of 10 so that we can really see it well. So let's go directly to the plot, and this is what it looks like. So this is the eigenvector corresponding to lambda 1. Okay? Notice that that is pointing in the direction of the major axis of the ellipse. Perhaps you don't remember what major, minor means for an ellipse. I still remember learning about that long ago in high school in my first algebra class. Second algebra class, excuse me. Sophomore year. And that's where that was explained to me. And basically what the major axis basically means, and if I were to draw, let's say, a dotted line here to represent that axis, here's also the minor axis. The larger axis, let's say, of that ellipse, that's the direction the eigenvector points to. And we see that on the plot. Or it points in that direction. I think that's a better way to put it. Then for that second eigenvalue and the corresponding eigenvector, notice how it's kind of pointing in the same direction that the minor axis of that ellipse also does. Okay. Now, we've done this kind of plot for a contour plot. We've done this kind of plot with the arrows as well. So I'm not going to go through the code here again. Let me see here. Yeah. How do we find then all the eigenvalues and eigenvectors from that covariance matrix? Well, we use the eigenfunction. Okay. Now let's do some what ifs here. And this is then really the reason why we're looking at this. Suppose I change that variance for x2 from 1.25. Let me just verify that. Yep. From 1.25 to 0.26. This is about as low as I can go for that variance and to still have this covariance matrix work out for me. Meaning, if you remember, the determinant of sigma has to be greater than 0. In this particular case, the determinant ends up being 1 times 0.26 minus 0.5 times 0.5, so we get 0.01. Now notice what this means when I have this alternative distribution. Look at my correlation. Whoa, that's 0.98 now. Before, I don't remember what it was. I don't even think I have it there, but it was positive. It was, I don't know, maybe 0.4? Okay, 0.45. Now we've really jacked up that correlation. We've really increased the relationship between x1 and x2. And again, what that means is that if I know x1, I should have a good idea what x2 is, and vice versa. Look what happens now to that contour plot. It gets compressed in the minor axis direction. That's kind of interesting. And let's just imagine, how about if I put these axes here again? You can see how those eigenvectors are all pointing in the correct directions. They're pointing, I guess different directions, but still in the direction of where you see the axes. Remember, these eigenvectors are not unique. So if I take -1 times 1, if I take -1 times one of them, notice what's going to happen. Then the eigenvector is just going to change where it's at. Okay? Oops. Okay. So I put the minor and the major axes there. And imagine, let's say, you can say, almost say, let's say, turning your head a little bit. So that indeed that this is, let's say, perfectly horizontal. This is then pointed directly up. And if you turn your head and imagine, let's say, that you have a new, let's say, x and y axis coordinate system corresponding to these axes. So maybe I'm going to call this now, how about if I just call it y1 and y2? Again, imagine a completely new coordinate system to do plots on that's tilted like this. We can see in this new system that if I want to understand eventually my data that I have, do I really need to know y2? The answer is no. Why? Y isn't WHY. Were you?
Like already correlate like high. If I know why, I can just do it.
Well, maybe let's think of it this way. Where would I expect most of my data values to fall? Their y2 isn't really going to change. It's only the y1. So what this says to me that if I want to think of this as a data problem and that I want to understand my data better, I can essentially reduce this from a two-dimensional problem to just a one-dimensional problem. Okay? That's very, very, very important. What if we have a trivariate normal distribution and we wanted to do a contour plot? Well, now we're going to have to go into 3D. So, I brought my football. Imagine that this is a three-dimensional contour just floating in space here. So maybe the outside of this football is f of x is equal to 0.01. If I had f of x equal to 0.001, I would have a larger football that goes around it. But this is now, let's say, an ellipsoid in space representing a contour corresponding to x. It's giving me values of f of x for x1, x2, and x3. Okay? You could have eigenvectors, let's say, poking out of the origin, going up, pointing towards, here's the major axis of that ellipsoid. We have two other axes here and here, because we're in 3D. Those axes are meant to be exactly the same size, if you think of it in terms of a football. Okay? So the eigenvalues for this and this corresponding here, those eigenvalues will be smaller than that vector that's pointing up towards that major axis. Okay? This, what I just described to you, corresponds to this case right there in terms of my lambdas. Lambda 1 is going to be greater than lambda 2 and lambda 3, and lambda 2 and lambda 3 are exactly the same value. Now, let's say that I squeeze a little bit of air out of this, so that, let's say, I make this axis, for that axis, for this axis, I'm going to make it not as important. So I squeeze a little bit air out of it. So imagine that you're Tom Brady, and, you don't like that football fully pumped up. If you remember from 10 years ago, it's been a while. Deflategate, it was called. Look it up. He didn't like footballs because he couldn't get his little hand around the football. So in that particular case, though, if I am, let's say, squeezing this down, now then my lambda 3 is going to be less than my lambda 2. Okay? That's going to then correspond to this particular case. And then if I, let's say, were to somehow squeeze all the air out, and I'm not going to do that with this, but instead I got this kind of a Nerf football here. So let's say I flatten this out completely. So I have no variability in one direction. That's going to mean my lambda 3 is going to be 0. And that corresponds to this. Okay? You could even squeeze even more. So I've squeezed this out here, and let's say I've even compressed this, so I basically almost just have a flat plane in space. Then that would be corresponding to lambda 1 is greater than lambda 2 is equal to lambda 3, which is equal to 0. We could go a little bit further. We could go to, let's say, suppose I have what's actually like a perfect sphere. So this is like a little Nerf ball from one of my kids. Perfect sphere, okay? Now that corresponds to, let's say, all the lambdas would be equal to one another. The variability in all three directions is exactly the same. And again, you could squeeze some of the air out, or I could just compress this, and then this will mean then now I have only 2 dimensions to worry about, and lambda 3 would be equal to 0. And you can keep on doing these things over and over again. So that's an interesting way to view the relationship of the eigenvalues, eigenvectors to sigma, and understanding what that multivariate normal distribution gives us. So just to emphasize the point, if I were to have a case that looks like this, where 2 of the lambdas are equal to 0, meaning I have no variability in 2 of the directions of that ellipsoid in space, that says to me, I could look at this stuff in, let's say, a new coordinate system, just like what we did with that 2-dimensional plot. Look at it with a new coordinate system and only have to worry about one, let's say, new variable. And I would know everything about all 3 variables. That concept is what we essentially do for principal component analysis. So if I have, let's say, in a more realistic setting, let's say I have 20 variables. It's going to be hard to plot 20 variables all at the same time. You'll see some ways to do it, actually. But as you might imagine, it's going to be harder to make sense of all 20 variables, make sense of all your data. But if, let's say, now you work with an estimated covariance matrix, you find all 20 eigenvalues, and you just find out that just 2 or 3 of the eigenvalues are greater than 0. All the other ones are really, really close to 0. What that tells you is that you could look at that 20-dimensional problem now in only 2 or 3 dimensions and not lose information about your data. That is what principal component analysis does. More on that in about a week or 2. Any questions? Okay. Let's just talk about what's next, and we will conclude class. So today, once again, I'm going to have to end my office hours early. I am so sorry that keeps on happening. Usually it's because of this whole budget problem. So I have a meeting at 2 o'clock in Keim Hall that I need to attend. I'm happy to stay here with you until 1:45 to answer any questions that you may have. If you really needed to talk to me today, I should be back in my office by 3:30. And if you really need to talk to me and you don't want to wait around on campus till 3:30, just let me know and we can set up something on Zoom. On Thursday, we will have our tests. Again, I will start making it available at 12:25 on my course website. Looking further ahead, we will discuss project number 1 on next Tuesday. And then even further ahead, test number 2 is scheduled for Thursday, October 23rd. Are there any questions? Okay, that's all for today.